All right, well, this is going to be probably the last one of these lessons I have time for today before the next class comes in, but we're talking about lesson 1-5 in Algebra 2, and it's solving equations or inequalities using graphs. So the first one that they start off with, it almost seems a little silly to do it this way, but I'll show it to you just so you have an idea. If you have a linear equation like 3x minus 7, and you set it equals 20, normally you would just add the 7 to the other side, get 27, divide by 3, and solve and get 9, right? Well, here's how they're suggesting you could also do this with graphs, is you put an equation for the left side, and then you have an equation for the right side, just the y equals 20. And after you do that, graph each of those, and where they intersect should be your solution, because that's what we're looking for, is where they equal each other, and where they intersect is where they equal. So 3x minus 7, go down your -7 for your y-intercept, slope of 3, up 3 over 1, put that line in there. Then for the y equals 20, just up 20, I shouldn't have went that high, I'm gonna go off my page. So you get up here, and then you're gonna put a horizontal line, because all the y's equal 20 on that horizontal line. Every one of the points on that line are up 20. Isn't that what y equals 20 means? No matter where you are, left or right, you have to go up 20. So if you look for this point right here where they intersect, and remember what we said? So you could do this on decimals, a graphing calculator sort of thing, a tool. Now, this point up here is the point 9, 20. I believe it's a 9. Didn't I say when we solved this, we got a 9? Add the 7 over there, don't I have 27? Then divide that by the 3. 27 divided by 3 should be a 9. So my x value here, right up there where they intersect, is a 9. Now, the reason some people will get this wrong is the 20, the y point, the y coordinate of that intersection up here, of that coordinate, is the 20 part of the solution? But if you go back to the original equation that's written over there in blue, do you see a y in that equation anywhere? I hope you say no, unless I just have bad handwriting. But if you do not see a y in the equation, then the y is not part of your solution. So this 20, we'll use that to help figure it out. We use the Cartesian coordinate, the xy axes, to find the solution. But really the only part of it that is the solution is the 9. Okay, so it seems a little silly because it seems like you could do this a whole lot faster just solving it with algebra, but they're using it as a lead-in so you can hopefully understand the next part. Because now when we go to the next part, some of them get a little more complicated where you can't use algebra to solve some of them. So the next one, they have something like an absolute value of x minus 4, and then they're going to set that equal to like a 1/2 x plus 1. And if you do this, well, how can you solve this one? Hopefully you caught on to the transformations in the other lessons. And on the left side of this, that minus 4 on the x will move the absolute value right 4. So if I come over on my axes and I go 4 to the right, and there's my absolute value of x minus 4. Well, now the other one, this one up here that I have in blue, my y-intercept of 1, a slope of 2, so over 2 up 1. So for this one, you should get 2 solutions there. So one of the solutions is right over here, looks like maybe 3-ish or so. I don't think 3 is exactly right because 3 times 1/2 is going to be 1 1/2. That'd be like 2 1/2. So my graph's probably off a little bit. But if we had like a Desmos program or something, we could probably solve it, figure it out. So from the graph, if you have technology or a little more accurate than mine, let's see, otherwise let's try this. If x minus 4 equals the 1/2 x plus 1, that should give us an answer that works. So if I add the 4 to the other side, I've got a 5 over here then. And if I subtract a 1/2 x from this x, that gives me a 1/2 x over here. And so a 1/2 times what number equals 5, or multiply both sides by 2? I'm going to guess that's that furthest point over here, because the one on the left looks like it's a long ways away from that. We'll check it out, see here. Now the other thing is, if this x minus 4 equals the other side, they would come out to solve and be equal. But what if the one in the x minus 4 is opposite? So what if the opposite of the x minus 4 equals the 1/2 x plus 1? So it's just showing you how algebraically we can also find a solution. I don't know that the book actually gives you this part, but as long as we're here, let's check it out. So we have a negative x, distribute that onto this minus 4, we'd have a plus 4, and then a 1/2 x plus 1. I'm going to subtract this 1 over here so my numbers stay positive. Add the x over there. 1 whole x added to a 1/2 x is 1.5 x. So 1/2 times what? 1.5 times what equals 3? I'm not really sure what that is, but I'm going to grab a calculator and just check it out and tell you. So I've got 3 divided by 1.5. Oh, so it's 2. We should have been able to figure that out. So this point right here is an x of 2. And that one up there of 10, you could plug them in and check it out. So if we're going to plug it in and check it out here, let's just do a little mental math with this. So first of all, I've got 2 minus 4, that'd be negative 2. Absolute value is 2. A 1/2 times 2 is 1, plus 1 is 2, so that checks. Let's try that 10 now and see. 10 minus 4, negative, or 10 minus 4, positive 6, absolute value is 6. A 1/2 of 10 is 5, plus 1 is 6. So it does appear that those did work. Okay, then the next example they're going to give us is they're going to ask us, what if we have a quadratic with an inequality? So let's just say we have, x plus 2, let's go x squared plus 2, and I want to know where that's greater. Let's maybe move it down. X plus a negative 2, x minus 2, where it's greater than 0. So again, transformations, x squared plus a negative 2, if that is too messy and somebody's having a hard time with that, let's just rewrite that so it looks right. So somebody doesn't get the wrong idea here. X minus 2, so that would be a parabola moved down 2, where it opens up, and greater than 0. So greater than 0, isn't 0 on the x-axis? So what parts of that graph are greater than 0? First of all, hopefully you would agree that it's going to be these arms that are sticking up here. Again, are the y's actually part of the solution? Hopefully you say no, the y's aren't part of the solution. There was no y in the original problem. So it's just the x's. And where do those x's occur? So what we're going to have to also figure out here is, what are those 2 x-intercept points there, or where is the graph 0? So when does x squared minus 2 equal 0? Add the 2 to the other side. Square root both sides. And you get the square root of 2 is what most students tell me on first glance. And then you look at the graph and you say, wait, there's supposed to be 2 answers. Well, why is there 2 answers? Well, I usually defer to an example like this. So x squared equals 25. If I asked you that, I like to use one that has a perfect square so you can do it in your head. And I asked you x squared equals 25, what's x? And most people, again, will say 5. And my response is, well, you got half the answer. Because what about, and somebody usually chimes in, and if they don't, I say, what about if I have a negative 5 squared? Isn't that also 25? And so usually students are convinced when I do square root both sides of an equation to solve here, I do need both a positive and a negative. So this is my negative square root of 2x intercept. On the right is my positive square root of 2 intercept. Now let's write, where is the graph? Again, our original question, where is the parabola greater than 0? And it was the arms. So that's going to be from this point going to the left, the negative square root of 2, and from the positive square root of 2 going to the right. How's that look in interval notation? Negative infinity, like you're reading a sentence. How far to the left it goes? Now, granted, these arms look like they go up more than to the left, but they do continue to the left and to the right as well forever because we don't have anything restricting or stopping the numbers that you can put in there. So it stops here at this negative square root of 2. Since I did not have an equal to on this original problem, the actual 0 itself is not included. So I'm going to put a parenthesis. Had there been an equal to under this inequality, that would have been a square bracket. And then because we have a solution in another area, the traditional or the, I don't know what you want to call it, the formal math symbol for if you have more than one solution is this capital U. I don't know that your book, it stands for the word union, kind of an old-fashioned word that meant like or. So your answers are there or they're over here for this going to the right forever as well. And so that's how that one would work when they just have a quadratic greater than or equal to another number. Sometimes they'll have where is a quadratic equal to something that's like, say, a line. So if I had this quadratic, x squared plus 5x plus 6, and I wanted to know when does that equal x minus 1. And so solving by graphing, you just graph each side separate. I don't know if you remember solving or factoring a quadratic. I think you guys had this. Would factor like that. 6 is 2 times 3, and 2x plus 3x makes that 5x in the middle. But for your x-intercepts, that's when these equal 0, because it's like y. So when does x plus 2 equal 0? That would be your negative 2. When does x plus 3 equal 0? That would be at negative 3. So, and it's a parabola opening up because the number in front of there, the coefficient on the x squared is positive. So we have a parabola that's just dipping down a little bit right in there. Well, now where's my x minus 1? Well, this graph, I might have made a problem that doesn't exist, because if I go down 1 and I have a slope of 1, looks to me like they never intersect. So we could check that on a graph. I'm going to do that quick. I got a graphing calculator sitting right here. I'll just tell you, I'm going to think that the little problem I made up, x squared plus 5x plus 6 and the x minus 1, I don't think they probably intersect ever. Let's just take a little look, and they certainly do not ever intersect. So this one would actually have no solution. Well, let's see if Mr. Gammon can do better on the next one. Or, you know what I can do is we'll just take this same exact problem and let's modify it so my line is kind of sloped in a negative direction. Then it should certainly go through there. So let's take this line out. Let's make my slope like a -1 there. So I still have my y-intercept there. And I still have a slope of -1. Now it certainly looks like it goes through there. Let's go back to that original problem and see what happens had we tried to solve that algebraically. We should get not possible. So if I do x squared plus 5x plus 6 equals my x minus 1 that I had, you know, bring that x over, that would be 4x. Add that 1 over, I'd have 7. If I try to solve this right now for x-intercepts, I think what we're going to find is we don't have any x-intercepts. That's what it equals 0 mean. When does it cross the x-axis? So let's try a little quadratic formula and see what happens. X, you know, a here is 1, b is the 4, c is the 7. So x equals -b plus or minus the square root of b squared, which would be 16, minus 4ac all over 2a. Look what happened under the square root there. So under the square root, we've got a square root of a negative, and in terms of real numbers, you can't do that. We can do imaginary numbers, and we'll see what those are after a while. But since there's no real numbers because of that. Let's go back and see what happened had we used the new one that I have that does look like they actually intersect. So on the new problem, where they intersect, let's try that all again. This time, I've got my original problem, x squared plus 5x plus 6 equals, and remember I put that negative slope on there, so a negative x minus 1. So for this one, when I add the 1x to the 5x, I've got a 6x, and when I add this one to the 6, I have a 7, my x squared. And for this one, let's see what happens if I do quadratic formula again. So I've got a of 1, b of 6, c of 7, x equals -b plus or minus the square root, b squared minus 4, a is 1, c 7, all over 2a, 2 times 1 is 2. So I've got 36 minus 28, so that would be a positive number under there, so it does exist. So in this case, I would get 2 solutions. I may not have a perfect square there because 36 minus 28 is just 8, right? So I've got a square root of 8 in there. But because it's positive, they do exist. We'd come up with probably 2 decimal approximate answers for x in this case. So that's how you would do that one. The last one would absolutely just require you to use some sort of technology. Because if on one side I have an absolute value, it's going to get too messy to do it by hand. And on the other side, so that problem is absolute value 2 to the right, correct? So it'd be like over here. And so then if I had a quadratic like that one, so if I factor that to find x-intercepts, x plus 3 and x minus 2, I believe. So I'd have an x-intercept of 2 and -3 there. And it's opening up. So one of the solutions we found, this one down here, but the one over here, that's going to be really messy to figure out from that equation. So graphing technology, Desmos, type in the 2 separate sides, look on the graph or graphing calculator for where you're going to find the solution. But that's all the parts of lesson 1-5, solving equations by graphing.